we're going to look at some nuclear reactions. And this part is so cool because, first of all, it's just cool that you can turn elements into other elements. But it's also cool because the math is so easy. I remember when we learned this, I was like, I cannot believe this is the last topic of general chemistry too. This is so cool because it's just doing adding and subtracting. And it's easy enough adding and subtracting. I can even just do it in my head. So it's a really, really great way to in Gen Chem 2, I always feel like. So the word decay, also the word emission, these are both used for these kinds of reactions, and they're primarily used with alpha decay, beta decay, and positron decay. So decays, emissions, that especially that word emissions, that should kind of make you think like something is going out or leaving, and that is what's happening. So these are the kind of decays that just naturally happen. They're just sitting there, and the sample is just like sitting there like in a bucket, and it's just randomly, based on its half-life, throwing out little particles. So it could be throwing out alpha particles, or could be throwing out beta particles, just throwing them out. So when we also don't, like, we have to know the reaction. We can't just predict, oh, that's going to be a helium alpha decay. We can't do it that way. We'd have to tell you. So this is a great part, though. Mass and energy are both conserved, and so it means that this top part is conserved across. So what you start with on the protons and neutrons together is what you end up with for protons and neutrons together. And then what you start with protons is what you end up with for protons. So essentially, our atom right here is throwing off a helium, and this is going to go flying away with energy. But remember, paper can stop us, so it's not that big of a deal. I mean, you know what I'm saying. It's a deal. You got to keep an eye on all types of radiation. But it's not as problematic for humans. It is problematic for plants, for sure. All right, so what we've got is I need this side to equal the left-hand side. So if it take 82 plus 2, that makes 84. So I'm good on that. And then the top, 234 plus 4 gives me 238. So basically my top numbers are equaling the top numbers and the bottom numbers are equaling the bottom numbers. Then I got to figure out what it is by just go to periodic chart. And down here is 82. So that's lead. Note another way you might see that problem, and we don't have this all, I don't have this all written in here, but what it could also be is these are the two products. It was an alpha decay. This is the product. It could say it that way and just say it was alpha decay. What did you start with? So you have to fill in this number, and that's okay. So if you don't know what this one is, but we know the right two ones, we can say, okay, 82 plus 2, that gives us 84. And on top, 238. And so then when we look this up, that tells us that that one is polonium. So you can do it either direction, and that's how these problems are written. And again, note that it's not going to be spelled out like this. It might just say PO undergoes, and it has to tell you which one. It could say PO 238 undergoes alpha decay. And that's all it has to tell you. That phrase alpha decay means alpha is one of the particles. You figure out the other particle. I've got some more examples here. Now, this is doing a beta decay. Note that this can also be written like in the problem, it might be written like that, or the phrase negatron might be used. But either way, the bottoms have to equal. Now, look what happens right here. 7 minus 1 is what gives me 6. So that one's slightly weird because you kind of have to think ahead. It's a number that's greater than 6. But once you get that, the top number on these, it takes a little extra thinking there, but then the top number is great because that's 0, so it stays 14. Then we look it up on the chart, and you'll see that nitrogen is 7. And then for right here, for the carbon one, and that's a +1. This is just normal. And again, you might see this as being positron, or in the problem, it might just say beta plus. So we can see that 1 plus 5 is 6, and 11 plus 0 is the carbon one. And again, if you aren't sure what it is, you just look on the periodic chart and you find it. And like I said, you might have to figure out this one rather than this one. But again, these are so nice and easy because you're just filling in the blank numbers on top and bottom and then looking at a periodic chart. Note, make sure your periodic chart has more than the bottom two rows. Sometimes we give these little shortened versions because we don't do a lot of chemistry in general chemistry with the lower section of the chart because it's radioactive. That's why. Now you know why. But you do want those bottom two rows, those lanthanides and actinides, because they do a lot of radiochemistry. Everything's radioactive down there, so they're often used as examples for these problems.